Hello everyone and welcome back to the iMachines TV channel. The construction progress of the Happisburg Sea Defense Project in Norfolk has been commendable, as efforts to protect the vulnerable coastline and combat erosion have shown promising results. The project, which has been underway for several years, aims to safeguard the local community from the increasing threat of rising sea levels and mitigate the adverse effects of coastal erosion. Extensive planning and research were carried out in the initial stages of the project. Detailed surveys of the coastline were conducted, and comprehensive environmental assessments were performed to understand the unique challenges faced by Happisburg. This thorough planning phase laid the groundwork for the subsequent construction efforts. One of the primary defense measures employed in the project is the construction of robust seawalls. These concrete barriers act as a physical shield against the powerful waves, reducing the impact of erosion and protecting the coastline from further degradation. The construction team prioritized the resilience and durability of these seawalls to ensure their long-term effectiveness. Another crucial aspect of the project involved the installation of groins along the coastline. These structures, made of wood or concrete, were strategically positioned perpendicular to the shore to disrupt the longshore sediment transport. By trapping sand and sediments, groins help build up the beach and stabilize the shoreline. This measure serves to dissipate wave energy and decrease the rate of erosion in Happisburg. Significant efforts were also made to replenish the beach with sand and gravel. Large quantities of these materials were carefully deposited along the coastline, helping to restore and widen the beach. This not only enhances the natural aesthetics of Happisburg, but also provides an additional buffer against erosion and contributes to the overall coastal resilience. The construction of the River Bridge pier foundations for the St. Croix crossing involved a meticulous process to ensure the bridge's stability and longevity. A precast cofferdam system was utilized, a first for Minnesota. The construction crews began by floating in a prefabricated steel framing system and pouring a concrete deck topping to create a work platform. 4 large circular holes were incorporated into the platform as guides for the steel casings, which formed the caissons. Each pier column required 4 caissons, resulting in a total of 10 pier columns in the river. The steel casings were inserted through the platform openings, extending through water, muck, sand, and gravel and soft sandstone until they reached the bedrock beneath the river. To clear the casings of materials, excavation tools were used while the water remained inside. To ensure a solid foundation, an additional 25 feet was drilled into the bedrock for each foundation using large drill bits. This process involved breaking up the rock, resulting in the removal of substantial amounts of sand, muck, and gravel. The caissons were positioned approximately 125 feet below the footing and about 150 feet below the water level. The pier columns stood taller, with heights ranging from 100 feet plus 67 feet for the Minnesota approach and 140 to 160 feet plus 67 feet for the Wisconsin side. Once the casings were clear, reinforcement bar cages were installed, and concrete was pumped into the casings to create stable foundations for the bridge. The next step was constructing footings above the caissons, acting as transitional components to the pier columns. To create a dry working area, a cofferdam was installed around the prefabricated deck and lowered to the river bottom. A concrete seal was poured underwater, followed by pumping out the water from the cofferdam. Within the dry area, reinforced concrete footings were constructed on top of the concrete seal. There were a total of 10 footings, with 2 at each of the 5 river piers. The construction crews then erected columns above each footing, capable of supporting a weight of 400,000 tons. Once the pier columns rose above the water's surface, the cofferdam walls were removed, allowing the water to surround each column. These underwater foundations were designed to endure a minimum of 100 years. By the end of this project, each of the 10 columns stood approximately 16 feet above the water's surface, signifying the completion of the work below the water. This progress allowed for the continuation of the construction, with the pier columns set to be extended to their full height, providing a visible representation of the bridge's development for the public to witness. St. Croix Crossing is a bridge that spans the St. Croix River, connecting the states of Minnesota and Wisconsin in the United States. It involved the collaboration of multiple agencies, including the Minnesota Department of Transportation, MNDOT, and the Wisconsin Department of Transportation, WisDOT. The primary objective was to replace the aging Stillwater lift bridge and enhance transportation efficiency in the region. The St. Croix Crossing is an elegant cable-stayed bridge featuring a striking design and state-of-the-art engineering techniques. Its main span stretches 1,050 feet, 320 meters, making it the second longest freestanding extradosed bridge in the world. The construction process involved precise planning and meticulous execution. Skilled workers and engineers utilized advanced construction techniques, including the use of self-propelled modular transporters to position the massive bridge segments. The project also emphasized environmental considerations to preserve the natural beauty of the area. The construction industry in Japan is renowned for its advanced technologies and engineering innovations, especially in the field of bridge construction. The Keisanuma Bay Crossing Bridge, built by Bridge Company, exemplifies the application of cutting-edge technologies throughout its construction process. This article explores the use of advanced bridge construction technologies, focusing on the main tower large block erection to the main girder closing of the Keisanuma Bay Crossing Bridge. Precasting and prefabrication. Precasting and prefabrication techniques play a vital role in bridge construction in Japan, enabling faster construction and improved quality control. In the case of the Keisanuma Bay Crossing Bridge, precasting is utilized for the construction of main tower large blocks. These large blocks are cast off-site in a controlled environment, allowing for precise fabrication and reducing construction time on-site. Prefabrication techniques also ensure higher quality and accuracy in the construction of bridge components. High-strength steel and composite materials. Japan has made significant advancements in the use of high-strength steel and composite materials in bridge construction. The Keisanuma Bay Crossing Bridge incorporates high-strength steel in its main towers, cable stays, and other structural components. This steel offers superior strength and durability, allowing for lighter bridge elements and increased load-bearing capacity. Composite materials, such as fiber-reinforced polymers, FRPs, are also utilized to enhance the bridge's structural performance and resistance to corrosion. Precise erection techniques. The erection of main tower large blocks is a critical stage in bridge construction, demanding precision and expertise. M-Bridge Company employs advanced erection techniques to ensure accurate alignment and secure connections. Computer-controlled lifting and positioning systems are used to lift the large blocks into place, with strict monitoring to achieve the required tolerances. This precise erection process guarantees the structural integrity and stability of the main towers. Post-tensioning technology. Post-tensioning is a widely used technique in Japanese bridge construction, providing enhanced structural performance and reducing material usage. In the construction of the Keisanuma Bay Crossing Bridge, post-tensioning is utilized to connect and strengthen various bridge elements. Post-tensioning tendons, typically composed of high-strength steel cables, are tensioned after the bridge components are in place. This technique optimizes load distribution, minimizes structural deflections, and increases the bridge's overall efficiency. Cable stay system. Cable stay technology is prominently featured in the Keisanuma Bay Crossing Bridge, showcasing Japan's expertise in this area. The bridge utilizes a cable stay system, where high-strength steel cables are anchored to the main towers and connected to the bridge deck. These cables transmit the bridge's weight and external forces to the towers, providing stability and reducing the need for additional supporting structures. The design of the cable stay system in the Keisanuma Bay Crossing Bridge ensures an elegant and efficient load distribution. Welding automation. Welding plays a crucial role in bridge construction, particularly during the main girder closing phase. Japan employs advanced welding automation technologies to achieve high-quality and efficient welds. In the case of the Keisanuma Bay Crossing Bridge, specialized welding robots are utilized to perform precise and consistent welds between the main girder sections. These robots are programmed to follow precise welding procedures, ensuring structural integrity and minimizing human error. Seismic isolation and resilience. Japan is renowned for its seismic isolation technologies, aiming to enhance the resilience of bridges in earthquake-prone areas. The Keisanuma Bay Crossing Bridge incorporates seismic isolation devices, such as rubber bearings and sliding bearings, to mitigate the effects of seismic forces. These devices absorb and dissipate seismic energy, reducing the transmission of vibrations to the superstructure and protecting. Japan has long been at the forefront of bridge engineering, consistently pushing the boundaries of innovation and technological advancements. In recent years, the country has witnessed remarkable achievements in bridge construction, with numerous projects showcasing Japan's commitment to excellence in infrastructure development. This article highlights some of Japan's notable bridge building achievements, showcasing specific figures that demonstrate the country's prowess in this field. Akashi Kaikyo Bridge. One of Japan's most iconic bridge projects is the Akashi Kaikyo Bridge, spanning the Akashi Strait and connecting the city of Kobe with Awaji Island. Completed in 1995, it held the title of the world's longest suspension bridge until 2020. The bridge boasts a main span length of 1,991 meters, 6,532 feet, and towers that soar to a height of 298 meters, 978 feet. It required around 181,000 tons of steel and over 1.4 million cubic meters of concrete for its construction. The Akashi Kaikyo Bridge is a testament to Japan's expertise in constructing monumental and technologically advanced bridge structures. Seto Ohashi Bridge. The Seto Ohashi Bridge is another notable achievement in Japan's bridge-building endeavors. Completed in 1988, this bridge system spans the Seto Inland Sea, connecting the islands of Honshu and Shikoku. With a total length of approximately 13.1 kilometers, 8.1 miles, it consists of 6 individual bridges, including both suspension and cable-stayed structures. The project required over 230,000 tons of steel and approximately 1.4 million cubic meters of concrete. The Seto Ohashi Bridge plays a vital role in connecting the regions and promoting economic development. Tatara Bridge. The Tatara Bridge, completed in 1999, is a testament to Japan's engineering prowess in cable-stayed bridge construction. Located in the city of Kobe, this bridge has a main span length of 890 meters, 2,920 feet, and stands at a height of 220 meters, 722 feet. It showcases Japan's utilization of advanced construction techniques and materials, including high-strength steel and seismic isolation technology. The Tatara Bridge serves as a vital transportation link and an architectural marvel, exemplifying Japan's commitment to innovation and excellence. Akashi Maiko Bridge. The Akashi Maiko Bridge, completed in 1998, is an impressive suspension bridge connecting the cities of Kobe and Akashi. It has a main span length of 1,280 meters, 4,200 feet, and towers reaching a height of 297 meters, 974 feet. The project required approximately 181,000 tons of steel and over 1.1 million cubic meters of concrete. This bridge stands as a testament to Japan's ability to construct large-scale suspension bridges with exceptional engineering precision. Shin Meishin Mukagawa Bridge. The Shin Meishin Mukagawa Bridge, completed in 2014, is an outstanding example of Japan's commitment to technological advancement and sustainability in bridge construction. This cable-stayed bridge, part of the Shin Meishin Expressway, utilizes advanced composite materials in its construction, reducing the overall weight and environmental impact. With a main span length of 330 meters, 1,083 feet, and a height of 142 meters, 466 feet, it showcases Japan's dedication to innovative and eco-friendly bridge design. Kobe-Awaji Naruto Expressway. The Kobe-Awaji Naruto Expressway is a major infrastructure project that includes several remarkable bridges. The Naruto Bridge, completed in 1985, is a suspension bridge with a main span length of 876 meters, 2,874 feet, while the Onaruto Bridge, completed in 1985, is a cable-stayed bridge with a main span length of 876 meters, 2,874 feet. These bridges, along with other viaducts and interchanges, contribute to the efficient transportation system in the region and reflect Japan's expertise in large-scale infrastructure development. The Tamai Expressway, connecting Tokyo and Nagoya, has been a vital artery of Japan, playing a significant role in the country's economic growth. However, after half a century since its opening, it faces various issues. The opening of the new Tamai Expressway is expected to not only address these problems, but also serve as a new transportation infrastructure with great potential. The construction of the new Tamai Expressway is being undertaken by the NEXCO Central Japan Hadanoki Construction Office. The section from the Shin-Hadano interchange to the Shizuoka Prefecture border spans approximately 14 kilometers. The design of this section aims to have gentler curves and slopes compared to the existing Tamai Expressway. As a result, about 80% of this challenging area, which passes through steep mountainous regions, consists of structures such as tunnels and bridges. Within this section, there are 6 tunnels with a total length of 9 kilometers, accounting for about 60% of the main route. In tunnel construction, mechanical drills and explosives are first used to break the hard rocks. The broken rocks are then transported outside, and the tunnels are excavated while reinforcing the walls with arched supports in concrete to prevent tunnel collapse. The first tunnel after the Shin-Hadano interchange is the Keianuma Tunnel, which has been completed for both the up and down directions. The Takamatsu Tunnel is a nearly 2,900-meter-long tunnel spanning Matsumachi and Yamakitacho. It has faced difficulties in construction due to fragile geological conditions, frequent collapses of excavation faces, and the occurrence of groundwater. The construction is being carried out in consultation with experts to overcome these technical challenges. Currently, approximately 50% of the excavation work has been completed. The Akasaka Tunnel is a 1,000-meter-long tunnel. The excavation using mechanical drills began in June 2021, and the upbound tunnel was opened in July 2022. The Furujuku Tunnel has already been completed, and the construction progress in the section between the Furujuku Tunnel and the Yugure Tunnel involves cutting through hard bedrock while diverting rivers. The Yugure Tunnel, approximately 2,100 meters long, has its entrance covered with a housing structure to mitigate noise and minimize environmental impact. About 70% of both up and down tunnels have been excavated. The Yaeyama Tunnel connects Kanagawa and Shizuoka prefectures, with the upbound tunnel opening in March 2020 and the downbound tunnel opening in May 2020. It is a rare balanced arch bridge structure with a span of 220 meters between the bridge piers when completed, and it combines steel and concrete in a composite structure. In addition to the tunnels, the new Tamai Expressway also includes 6 bridges, accounting for about 20% of the main route's length. Construction techniques vary depending on the specific location and geological conditions. For example, the Nakatsugawa Bridge employs a bridge pier layout to avoid faults along the river. The Takizawa River Bridge uses a combination of steel and concrete in a composite structure with a reinforced buried frame to enhance durability and improve work efficiency. Transporting large amounts of earth and sand generated at construction sites is achieved through the reuse of materials in the new Tamai Expressway construction, reducing construction costs. To alleviate traffic congestion on national roads, belt conveyors are used in conjunction with high-speed highways for material transportation. The construction of the new Tamai Expressway not only focuses on engineering aspects, but also emphasizes community engagement. Site visits are organized to deepen interactions with local residents along the route.